So, 11.3 notes. We are learning about acids and bases. Last few class periods, we just started talking about solutions in general. So just a quick review. What are solutions? There should be some sort of solute. That one should really be silenced. Dissolved in solvent. So solute could just be anything like salt, sugar, things like that can dissolve. And solvent, probably something more like water. So then we had some vocab terms that are just more like, what if something is more concentrated? What if something's more dilute? So concentrated just meant that we had more solute in there. Dilute tended to mean that we had less solute per solvent in there. And if we were to dilute something in general, normally we dilute something by just adding some more solvent, like more water to something. The other thing that we talked about was like concentration in general. We said concentration was something that we measured in molarity or moles per liter. And it's moles of solute divided by liters of solution. So that is something that was really important that we talked about as well. Finally, we did some sort of dilution calculations, where we said that if we were to dilute something, we can calculate that exact volume that we would need to dilute to, or the exact molarity that we would have at the end if we just use this equation, where we have the initial molarity times the initial volume is equal to the final molarity times the final volume. All right, any questions from the notes before? All right, so that brings us to our next topic, acids and bases. So before we talk too much about acids and bases, I just want you to think about any times you heard about in your life about things that were considered acidic, or maybe you've even heard of people talk about like alkaline things, like maybe alkaline water, things like that. So what we're going to learn today in class is the exact chemistry definition of what's acidic and what's basic. All right. So first of all, what are acids and bases? Well, acids and bases, things that you might experience with acids and bases are, I think, the taste. Any food-safe acids and bases have very distinctive tastes. So acids tend to be sour. I want you to think of things like lemon juice or vinegar. Those are pretty good examples of acids in your life. And bases tend to be bitter and slippery. So things that might be bases are things like baking soda, kind of bitter, bar soap, like old-fashioned bar soap, not like Dove bar soap, or things like bleach. All right, so these are examples from day-to-day lives right now. But back then, when scientists were trying to determine what's acidic and what's basic, well, they were basically noticing that there seemed to be two categories of chemicals that always react in very similar ways. And they call these categories acids and bases. So the first scientist that started defining these categories was someone called Arrhenius. And he said, well, acids seem to produce H plus in aqueous solution, and bases seem to produce OH minus in aqueous solution. So basically, let's kind of review what it means to dissolve things and produce like ions in solution. If I have something like table salt, like NaCl, if that dissolves in solution, it kind of, we call it dissociates. It dissociates into these two ions, Na plus and Cl minus. If something like HCl were to dissolve in water, it also dissociates into like H plus and Cl minus. So if something dissociates and produces this H plus, RNA said that's an acid. Now, if something dissociates and produces an OH minus, like NaOH dissociating into Na plus and OH minus, RNA said, well, since it made that OH minus, that's a base. So that was his definition there. Another definition that came along later is a little more accurate. We're going to skip this Lewis definition. What is the definitions from Bronsted and Lowry? Two chemists here that said, well, maybe RNase's definition doesn't always work. So a good definition for an acid would be anything that donates a proton. By the way, proton means the exact same thing as H plus. And Bronsted-Lowry said, well, a base, which should be the opposite of that, is anything that accepts or absorbs a proton. So whether that be from its surroundings or from another chemical, anything that's able to like absorb a proton is going to be a base. So these are basically what acids and bases are. We're going to talk about what that might look like with numbers and different characteristics of these. So both of them are electrolytes. So if they're dissolved in water, they should start conducting electricity. Acids also react with bases to produce a water molecule and some salt. So when I say some salt, I really just mean an ionic compound. Anything like NaCl, CaBr2, those are ionic compounds, right? So for example, if I have NaOH, okay, it looks like a base there because there's OH, and I have H2S, okay, it looks like acid there because there's H in front. That produces a water molecule and some sort of salt, this Na2S. A base does the opposite here. A base reacts with acid, well, actually does the exact same thing, but it reacts with acid to produce a water molecule and some salt as well. And whenever an acid or a base reacts in this way, we do call it either an acid-base reaction or a neutralization reaction. So something that we probably learned about very beginning of the year when we talked about very beginning of the semester when we talked about types of reactions. So another example here, okay, we have magnesium hydroxide. Looks like the OH part of there, it makes it a base. Looks like the H part of that makes it an acid, and it forms some salt and some water molecule. The other thing about acids is that they do react with metals. Okay, we don't need to know the details of that, but generally all metals will react with most acids, at least over time. So question for y'all, soda is pretty acidic. Most sodas are pretty acidic. So aluminum, for the purpose of this acid reaction, aluminum does react with acid. So why doesn't soda react with aluminum in aluminum cans? Why is it not like dissolving whole or breaking down or chemically reacting and forming a hole in these like aluminum cans? Why don't we, when we taste soda from aluminum can, why doesn't it taste completely like aluminum? What's going on there? Acids are supposed to react with metals, and sodas are really acidic. So are aluminum cans fully aluminum? Is there any other components of them, do you think? I don't know if a lot of you are aware of this, but the inside of aluminum cans is actually completely coated with like plastic. So, if you're like avoiding plastics, you're like, oh, I just don't want to have any microplastics in my life. And you drink out of aluminum cans, congrats, you are drinking microplastics because it's all coated with plastic, but that stops that acidic soda from reacting with the aluminum and breaking down the can. So really the only way to avoid that is glass bottles. Kind of heavy and annoying to deal with. Can you open that? Sorry. Okay. So we are going to skip this explanation of strong versus weak acids and bases, but we are going to talk about when an acid or base dissociates really quick. So when an acid or base dissociates, the acid or base splits into its ions. And that's just kind of what we were showing before, whenever it's dissolved in water. So for example, if we have H2S, when I look at this, I'm like, well, maybe H will split off into H plus and S will split off into this S2 minus. So we're going to have two of these H pluses just kind of dissociate off. They'll ionize off. And it will be floating around with this S2 minus ion in water. When we have a base, it'll do the exact same thing. When it dissolves, it kind of like splits off into its individual ions. So aluminum will split off into an aluminum 3+, and a hydroxide will split off into an OH minus. But there were 3 of them, so make sure we write down 3 OH minuses. All right, questions so far? So I'm not going to make you memorize like what strong acid, what strong base, or what the names of anything are this year. But what I'd like you to do is go ahead and try to notice like the format of what an acid or a base looks like. So notice most of these acids, they tend to have like an H in front. That's most of the acids in this class will have a very obvious H in front. You can tell it's an acid just because of that. And then the names of these acids seem to be based off of the elements or ions that they're paired with. So for example, if I'm with Cl, it looks like I'm called hydrochloric acid. Okay, chlorine for chlorine, it seems like. If I'm an H with a Br, it looks like I'm called hydrobromic acid. Okay, bromic for bromine. And then you might also notice things like if I have an H with an NO3 or a nitrate, we're going to call that nitric acid. So it seems like the names are kind of based off of what it's with. Notice here that the strong bases, or just bases in general, they tend to have OH in them. So we learned about chemical naming before last semester, and we said, well, this stuff was called hydroxides. And we just had, the element name in front and then hydroxide at the end. So LiOH, that's lithium hydroxide. Something like KOH would be like potassium hydroxide. So just kind of going down here to Arrhenius acid-base theory. An acid is any substance that can produce H plus in water. Often it'll be written with an H in front. And a substance that produces OH minus in water should be a base. So just kind of going off of this theory, it's a really, really simple theory to follow. And just kind of look at a chemical formula and tell if it's an acid or a base. So let's try to do that right now. Let's try to categorize the following compounds as an acid, a base, some salt, or neither. Neither meaning none of the above in this case. So what do we think HCl is? Probably going to be an acid because there's an H in front that gives off H plus in water. What do we think K2SO4 might be? So I don't see H in front of it. I don't see OH minus in it. Could it be salt? When I say salt, that is an ionic compound. So does it seem like an ionic compound? Yes, it does. There's a metal and a polyatomic ion in there. K is a metal, SO4 is a polyatomic ion. This would be salt. Some sort of salt, right? Not just table salt. All right, what do we think about CH4? What could that be? I notice there's H in there, but it's H in front. So this is actually the formula for natural gas or methane. This does not behave as an acid. So notice that just because something contains H doesn't mean that it's acidic. So it's not written in front. It doesn't seem like it's basic either because there's no OH minus in it. And it doesn't seem ionic to me because it's a nonmetal with a nonmetal. So I'm going to say probably neither, like none of the above here. What do we think HC2H3O2 is? Probably an acid. There's that random H in front. And indeed, that is the case. This is called acetic acid. It's actually the formula for vinegar. What do we think about NaOH? Probably a base. I agree. Because there is OH in there. So according to Arrhenius' definition, it should be a base. Finally, we have CuCN2. What do we think that is? This one is going to be salt because it is an ionic compound with the copper metal and the Cn polyatomic ion. Questions so far? Okay, so the thing about this theory here that's really easy to see if something's an acid or a base is the fact that we have something like ammonia in existence. And ammonia is a great household cleaning chemical. The thing about ammonia is it's actually a pretty strong base, but I don't see anything that indicates that it could be a base. So this is actually a base. And the reason why it's a base is because according to the Bronsted-Lowry definition of bases, it would accept a proton and act basic. But there's no OH minus, so according to Arrhenius, it's not a base, which is not a great definition for base. So let's review Bronsted-Lowry. An acid is a substance that can donate a proton or give any sort of H plus, right? So we can call it a proton donator. What's left over from that acid, we're going to call the conjugate base. And we'll talk about that in a moment. A base is something that can accept a proton. So it's absorbing protons. So we're going to call it a proton acceptor. And then whatever is left over from the base, we're going to call the conjugate acid and talk about that again in just a sec. So please also remember that protons, hydrogen ions, and H plus, that all means the exact same thing in this class, in chemistry in general. What we want to do here is let's go ahead and look at a couple of examples of chemical equations and label everything as the acid, the base, and then the conjugate acid and the conjugate base. And we're going to make sure we're able to identify that. So over here, before I even try to label anything, I have HCl plus H2O. Let's try to figure out what's going on here. Something happens to this stuff so that now I have H3O plus and Cl minus. So what I'm thinking happens is that HCl seems to give a proton or an H plus to H2O. And now it seems like HCl became this Cl minus, and it seems like H2O became this H3O plus. Okay, so if HCl gives away a proton and H2O seems to accept a proton, what is the what is the acid here, according to Bronsted-lowry? HCl or H2O? It would be HCl, exactly. And that means, of course, the base has to be the other one, H2O. And the reason why H2O is the base is because it accepted a proton. It absorbed that H plus. Okay, so there's two different ways to think of the conjugate base and conjugate acid. You can think about it as like, what is left over of the acid is now the base. What's left over of the base is now the acid. I find that definition kind of confusing. I'm going to tell you the way I think about it. So when I think of conjugate, I think of like, okay, it's probably like the opposite on the other side somehow. So I like to do this. I like to imagine this chemical reaction is kind of going in reverse. And I'm like, if this chemical reaction were to go in reverse, who's going to have to donate the proton and who's going to have to accept the proton to get to the left side of the equation? So I'm like, how do I get from H3O plus to H2O? Well, I probably have to donate a proton from H3O plus. And how do I get from Cl minus to HCl? Well, I probably have to accept that H. I probably have to accept that proton from H3O plus. So if you're thinking about like, what has to happen to go in reverse, you can use this exact same definition of acid and base. So since H3O plus would have to give away an H plus, do you think it's going to be the conjugate base or conjugate acid? It would probably be the acid. So H3O plus is indeed the conjugate acid there, which means Cl minus, which would have to accept the H plus in order to get back to where we started, would be the conjugate base. Excuse me. Questions so far? All right, let's look at another equation here to see what's up. So in this case, we do have like this kind of reversible arrow kind of thing going on, but just treat it exactly the same way as before. That's more advanced chemistry there. And now we have NH3, ammonia, like what we saw before, reacting with H2O to form NH4 with a plus charge and OH minus. So just take a moment and try to think about what's the difference between start and after, like what's going on. To me, it looks like okay, NH3 got a brand new H. Okay, makes sense. And it looks like H2O lost an H. So if I were to visualize that, I'd probably write it out like, H2O gave up this like proton, this H plus, and probably gave it to NH3. And now I have my result there. So just thinking about, which one gave a proton and which one accepted a proton. Which one do you think is the base, NH3 or H2O? Which one accepted the proton? The NH3 accepted the proton, so it is the base, which means the acid has to be H2O. Okay, now thinking about it in reverse, like what has to happen for us to reverse this stuff? That's going to be the conjugate base and conjugate acid. So in reverse, how do I get from NH4 plus to the NH3? I probably have to remove one of those H pluses there. So I'd probably remove it and give it to this OH minus. So thinking about that in reverse, what do you think the conjugate base is? What's accepting the proton? OH minus. The conjugate base is OH minus, which means the conjugate acid has to be this NH4 with that plus charge. Okay, questions on like kind of what an acid is, what a base is, and then conjugate acid, conjugate base. Okay, so I will say that in high school level chemistry, the Arrhenius definition is the most common. It's the easiest way to tell if something's an acid or a base. And you just see if something has H in front or OH minus at the back. Easiest way to tell if something's an acid or a base. All right, well, we will skip this nomenclature page. We kind of passed our naming unit, and I'm not going to make you name more stuff at this point. But if you're curious on all the rules to name acids, it will be in the answer key that we'll post in Canvas. Wait. All right, so before we move on to this next section, I want you all to make sure you have a yellow calculator on your desk. I want you to try out a lot of these calculations on your own using these calculators. Before we continue though, we will take a 5 or 6 minute break or so. So during that break, you can get a calculator if you don't have one yet. All right, we'll continue in a bit. All right, let's resume here. Hopefully, you all have a calculator. Let's talk about something called the pH scale. So, another thing I don't think a lot of y'all are familiar with, but it's quite commonly used whenever you talk about acids and bases. Just like before, when we talked about solutions like seem concentrated or more dilute, and then we're like, but let's put a number to it. With acids and bases, it could be more acidic or more basic, but we can also put a number to this. So the number that we tend to put to how acidic or how basic something is on something called the pH scale. And here's an example of a pH scale right here. But if you go to the next page, there's a bigger kind of pH scale where you notice that it tends to be 7 in the middle. And then we go all the way up to 14 and all the way down to like 0 or 1. And the way you read a pH scale is like the smaller the number, the more you go towards 0, the more acidic your chemical is or your solution is. And the higher you go, above 7, the closer you are to 14, the more basic or alkaline your solution is. So the more acidic or basic your solution or chemical mixture is, I guess the more chemically reactive you could say it is, the more dangerous it is. So for instance, you could have something that's just a little acidic like coffee, or you could have something super acidic like stomach acid or battery acid. You could have something just a little basic like baking soda, or you could have something super basic like bleach or drain cleaner. So those things are pretty caustic and can start like eating through organic matter. And then the only thing that's really neutral is completely pure water. So notice that neutral is at 7. Something else I want you to notice about the pH scale is that as you go down the pH scale, it looks like the H plus concentration and molarity and the OH concentration are changing. It looks like the H plus concentration goes up by times 10 every single time. And it looks like the OH minus concentration goes up times 10 every time you go up the pH scale as well. So whenever you go up in pH, it seems like OH, the amount of OH goes up. Whenever you go down in pH, it seems like the opposite happens, and then the amount of H plus goes up. So just knowing that, let's look at the definitions back on the last page. Okay, so what is the definition of everything going on here? Well, notice that the concentrations of H plus in solution and the OH minus in solution, they went up or down by times 10 for every single pH number. So whenever you have something that's like increasing or decreasing in increments of like times 10, we might call that something called like a logarithmic scale, not just like a linear scale. So if something's a logarithmic scale, we probably need logarithms to describe this stuff. You're probably just learning about this in math. I'm not sure where you are in math right now, but the definition of pH is it is the negative logarithm of the concentration of H plus. So whenever you have these brackets here, that stands for concentration in molarity. And then we have this very related concept called POH that simply is the negative logarithm of the concentration of OH minus. So we saw this on our pH scales, but basically, if our pH is below 7, we consider that solution acidic. And the amount of H plus we have should be greater than the amount of OH minus that we have. If our pH is above 7, we say our solution is basic or alkaline, and the amount of OH minus will be more than the amount of H plus that we have. Finally, if both amounts are equal, then we say our pH is 7, and the solution is going to be neutral. So we were kind of verbalizing this before, but basically, if the pH is increasing, if it's going up in number, then we can say it's getting more basic. So the amount of OH minus is going up, and the amount of H plus is going down. If we say the pH of the solution is decreasing, or the numbers are getting smaller on that pH scale, we could say that the amount of OH is going down, or it's because the amount of H plus is going up. Okay, so we didn't really learn about the definition differences between strong acid and strong base too much, but we can talk about the qualitative pH, like what the pH should be if you talked about a strong acid or a strong base. So strong acid, we're going to say it's really close to 0. It would have a pH of around 0 to 2. A strong base, we're going to say it's really close to 14. Probably will be around 12 to 14. Meanwhile, a weak acid will probably have something that's below 7, but not too low. So maybe somewhere between like 2 and 6.9. And a weak base will be something kind of above 7, so it's basic, but not too high, so probably something like 7.1 to 12 would be a weak base. So that's around where you can expect your pH levels to be if you're trying to compare strong acid versus weak acid versus weak base versus strong base. All right, the final part of our lesson here is we want to know all of these mathematical relationships and be able to use them to calculate missing pieces of data here. So all the data points that we should be able to convert between are pH, pOH, the concentration of H plus, and the concentration of OH minus. So this will look like a lot, but it's actually very straightforward if you just follow the formulas and make sure you know how to plug this stuff into a calculator. So as long as you don't lose these notes, you will be able to use this on your test. Totally fine with me. Um, these are definitions here. We learned about two of them already. Another really helpful definition to convert between one and the other is this one right here. We say that when you add pH and pOH, the total result's always 14. So if you have one and you don't have the other, you just subtract it from 14 and you get the other one. So that one's a pretty good definition to use. The other definitions, these other mathematical relationships we want to know are, well, what if we have the pH and we want to know the concentration of H plus? Well, then we do 10 to the power of negative pH, and then you get the concentration of H plus. Really similarly here, if you have the pOH and you want to get the concentration of OH minus, you do 10 to the power of negative pOH, and then you get the concentration of OH minus. This last definition here, we're not going to talk about too much, but it's also valid. If you want to get from concentration of H plus to concentration of OH minus, you can use algebra and use the fact that if you multiply those two concentrations with each other, you should always get 1 times 10 to the power of negative 14. Don't worry about that one too much. I personally don't use it too much, but it is valid. Okay, so I'm going to do a couple of these rows of problems with you, and I want you to fill out the rest and do the rest of the practice on your own or with a partner. So just showing what's going on here. First of all, this first row, this first sample, if the pH is 5.2, do you think this is acidic, basic, or neutral? Probably acidic, because the pH is below 7. All right, secondly, let's go ahead and calculate these 3 missing boxes here. So let's just take it one by one, step at a time. So if we have pH and we're looking for pOH, there is one relationship we could use here. This pH plus pOH is equal to 14. So if I just rearrange that a little bit, I know that pOH is equal to 14 minus my pH. Clear on that? Let's just rearranging it a little bit. So if I take my pH that I already have, this 5.2, and subtract it from 14, what should my pOH be? Like 8.8, right? I think so, something like that. All right, and that's all you do to solve pOH if you already have pH. So a little harder here. How would we get like the concentration of H plus from the pH here? Well, we could use this mathematical relationship in the top right, where we have concentration of H plus is equal to 10 to the power of negative pH. So this is where I want you to make sure that you know how to plug this into a calculator. This one's a simpler one to plug into the calculator, but I still want you to make sure you know that. So we can do 10 to the power of negative 5.2, because that was our pH. And then we should get a certain number here. I actually think your calculator spits this out in a really annoying way, but it'll be, if you write down what you get, it'll be fine. All right, so your calculator might look something like 0.00000 6, I think. So that's what your calculator would show. What I'm going to write down is just using scientific notation. It'd be 6.3 times 10 to the power of negative 6. Should mean the same thing. It's a little cleaner and easier to read, but you know, I actually don't. I actually don't know how to force your these like new calculators to show scientific notation. Um, but just know that, that is what the equivalent should be. All right, let's do the same with the concentration of OH minus. Very similar way we can do this here. The concentration of OH minus is just equal to 10 to the power of negative POH. So you can just do 10 to the power of negative, what did we get, like 8.8, and get our answer there. Just make sure you're able to get an accurate result there. We'll compare our answers. So your calculator should hopefully spit out a number like 1.6 e minus 9-ish. So I'm going to write this down as 1.6 times 10 to the power of negative 9 molar of OH minus. We're getting this? Yes? Okay, awesome. So that is the correct result there. Any questions so far, y'all? So I'm just using the equations available to me right above that table. What I want to do now is let's get down to the third row. This will be the last one I'll do is last one I do with y'all. But now what we're given is just the concentration of H plus, and that's it. Okay, so there are a few things I could do here. I could try to get the pH from that. I could try to get the OH from that right away. Honestly, I'm more comfortable trying to get the pH from that. So this is the part that's messing up a lot of people. Like, if you haven't been using your calculator so far, please try to use it right now. How do you plug this into your calculator? So the definition of pH is it's the negative logarithm of the concentration of OH minus, or sorry, of H plus. So in your calculator, there are a few things I want to make sure you're able to do. First of all, remember to plug in your negative button first. Second of all, can you pull up that logarithm function? So you might have to use that control button on your calculator and then find where it says like log. Third of all, your calculator is probably going to force you to put like a base number into the logarithm. So when I say base number, it's like some random number on the bottom here. So the number that we're looking for here is the base 10. So whenever you have to fill out that random bottom middle number, you can plug in a 10 into that. And then for concentration of H plus, well, we should already have that, right, from our table already. So your pH should be equal to negative log base 10 of this 5.6 times 10 to the power of negative 8 number. And you can plug that in, whatever preference you'd like, as long as you do end parentheses, it should turn out okay. And that means our pH is equal to, hopefully we all get the same number here. If you're using your calculator correctly, it should be about probably 7.25, but I'm going to write down 7.3. I'll round it just a little. Anyone need help at this point with your calculators? You're able to get this number? Awesome. Yes, what's up? Yeah, on that bottom blank, that's where you put 10. And then on the right blank, that's where you put that 5.6 times 10 to the power negative 8, and then in all that in parentheses. It's probably already going to be in parentheses, yeah. Anyone else have questions on these calculations? Okay. So I would say that's the one thing that's tripping people up the most on these calculators. These are the only calculators you're allowed to use in the test, so just make sure you're able to do that. Okay, filling up the rest of this table really quick. It's pretty simple, pretty trivial, just using the same exact skills that we used in row 1. For example, We know that POH is just equal to 14 minus our pH. So 14 minus 7.3. What is that, like 6.7? Easy peasy. And then concentration of OH minus, we can kind of copy our work from before. It's just going to be a different number here. We can say, oh, it's going to be 10 to the power of negative POH. So 10 to the power of negative 6.7. You might get 1.99 something something. I'm going to write it out as 2.0 times 10 to the power of negative 7 molar. So of course, you don't have to write down every single step every time. I just write it out at first, so you know what's going on. Finally, do you think this is acidic, basic, or neutral? I just like to look at the pH for this. So it looks a little above 7. So I'm thinking this is basic. All right, y'all. So as I mentioned, our test is next class period. That'll be over 11.1, 11.2, and what we just learned here. For practice, for reinforcement here, just to make sure you know how to calculate this stuff, go ahead and try out row 2 and row 4 on your own. When you're done with that, when you feel like you're in a good spot, you can go ahead and start your test review, which is stapled to the back of your notes. All right. I will grade your practices and test review for completion grade on test day. So make sure if you're not done with anything, make sure you get done with it tonight and tomorrow night. All right. All right. Let me know if you have any questions. I'm going to go ahead and conclude the notes here and post this video.